All right, welcome everyone. We are going to be talking more about convolutions today. But first, by way of announcement, Lab 3 is due this Saturday. I saw a comment on Slack about not being able to connect to Colab runtime. Has anyone else been having trouble with that? A couple of people. Have you been able to connect today? Yeah. You have today? Okay. Yeah, I want to be careful with this because the expectation is that you start the labs in advance. And for labs like this one, where training doesn't take more than a couple of minutes, you shouldn't need to upgrade to a Colab Pro runtime yet. That will start with Lab 4, where we're doing cancer detection. So yeah, that lab will take a little longer to train. And so the recommendation is that you pay the $10 a month for the remainder of the course to get access to longer run times and more priority access to GPUs. If you find that there's like a stretch of like 3 days from Thursday to the end of the week when the lab is due, when you just cannot connect to a Colab runtime, let me know and we can see if we can make adjustments. But yeah, I mean that's it on that front. Any other questions on the lab? Yeah.
There's also competitors to the lab.
Really? Cool. Yeah. What you said there are other alternatives?
Yeah.
So Gradient, my favorite space. Okay.
Yeah. Any cloud too long.
Okay, yeah, so it sounds like there are some alternatives as well. I think I've also heard that Kaggle has a similar Colab alternative, so you might look into that. Yeah, Brandon.
So how much are part of the testing is that we're trying to get at least one experiment where we run with over 1 million parameters. But do we have to demonstrate that particular experiment, or because that one didn't get 85% accuracy? So,
Gotcha. I mean, I would guess that with more parameters, you should be able to get a higher accuracy. You just train for longer. But if you're running into trouble with that, I think, yeah, just printing the number of model parameters should be fine. Okay. Yeah, question. The model with 1 million parameters ran out of RAM GPU RAM or normal RAM. Okay, that shouldn't happen. You should definitely be able to fit 1 million parameters in GPU. So if you're still having, I would talk to the TAs and they can help you do that stuff. All right. Yeah, Dan King.
One of the sections had this complete Xavier initialization, but
yeah.
The link provides 4 permutations of what that might look like. Does it matter which one we use?
No. Okay. Although I don't know. Yeah, I haven't looked at and done the lab recently, so I don't know what those 4 different ways are.
They're fairly similar. They're just nuanced differences. One uses the input layer count, the other uses the output layer count. A few coefficients are sort of.
Okay, yeah, either of those is probably fine. We have lots to cover today. We're hoping to cover initialization and activation functions and finishing up nets. So let's get started. So where we left off last time was we did our example of hand coding convolutional classifier for the number 7. So now we are going to talk a little bit more about the intuition of why these convolutions work. And also the example that we did not have any activation functions. But in reality, when we set up a convolutional neural network, we will stack convolutional layers followed by ReLU layers, etc., as you normally would. So this is a visualization similar to the visualization we saw from DeepViz, where you are visualizing the features learned by different filters at different stages of the network. And these images were obtained by optimizing, instead of optimizing over the weights of the neural network, optimizing the input image to maximize a certain filter. And these were the results. And so you see that the early filters in the network learn very simple gradients of color or repeated patterns of lines. Whereas as you get to the middle of the network, you're starting to learn higher level features where you have, more lines or a corner or nested circles. That kind of looks like an eyeball. And some other things that I don't really know how I would interpret. And then finally, at the last layers of the network, you're finding these really interesting, complex patterns like what looks like a sunburst and a honeycomb. So basically, the intuition for what's happening. Well, yeah. Does any ideas for what the intuition might be for learning these different types of features at different stages of the neural network? Yes, Spencer. So yeah, that's one idea, replicating how our brains process images at lower levels and then medium levels and then more abstract features. So I thought, yeah. Why do you think the loss function of maximizing the likelihood of a true class would end up with a neural network that learns these types of features? Yeah. Yeah, I think that's a great way of putting it. This is the shortest path that the network can find to correctly maximizing the likelihood of the true class. Yeah, Spencer. That's a really interesting question. So the question is whether different networks trained on the same data set end up converging to learning the same features. And the answer is yes, which is really interesting. And actually, there are interesting examples where we'll see later in the class where deep learning practitioners have figured out how to provide adversarial inputs to a neural network to cause it to misclassify something by introducing changes that are imperceptible to the human eye, but which the neural network schemes are very important. They're able to basically modify the inputs so that neural networks are totally confused. And the amazing thing about that is that these adversarial perturbations apply across different networks and often even different network architectures and often even trained on different data sets. So that's just kind of an interesting thing of where, there seems to be some sort of convergence to recognizing certain features and being confused in the same things. So yeah, and this is just a diagram kind of explaining that thing that we were just discussing of that idea of the networks learning a hierarchy of features. Then this is just the mathematical interpretation of what a convolutional layer is doing. And you don't need to worry too much about this, but in math, there's an operation called convolution. And you can imagine it as basically a sliding dot. I think of it as a sliding dot product where you, where you take what's called a filter and you slide it across a certain input window, whether that's over audio or an image, and it basically recognizes features across the vector that's being scanned against. And convolutions have been around for a long time in the field of signal processing, and this is just kind of a neural network learned version of those convolutions. Another example of features learned at lower levels and higher levels. And then this section we're going to go, oh yeah, question. How does a value layer work with the convolutional layer? Good question. So basically the same as it would with any other type of layer. So the output of a convolutional layer can be positive or negative, and all the negative values get smushed to 0, and all the positive values continue unchanged. So yeah, we talked a lot about the different ways that we can apply strides and padding to change the size of our output of our filter. And so we're going to look at that a little more here. So this is a 7x7 input with a 3x3 filter with a stride of 1. And it just scans across the image, and we get a 5x5 output if we don't have any padding. Does that make sense to everyone? How this input with this filter, it gives us a 5x5 output. What if the input was 8x8? What size would our output be? 6x6, right? Now this is a 7x7 input and a 3x3 filter applied with stride 2. We get what size output? 3x3. Now, if we do a stride 3, a stride 3 convolution on this, we are going to be losing information off of the side of our image because we aren't able to involve that filter with that remaining column. And so you can summarize this into a formula where the number of output channel, or the output size in a certain dimension, height or width, is going to be the number in the length in the input image minus the size of the filter divided by the stride plus 1. And so you see here n equals 7, f equals 3. We have stride 1, the output size is 5. Stride 2, the output size is 3. Stride 3, we get an uneven output size and end up losing some information. So we mentioned padding, adding zeros around the border of your input, and that enables you to preserve the size of the input if you maintain the stride. And we can also add padding into our output dimension formula, which we'll see at the end of these slides. Oh yeah, question. You're talking about like the wrapping idea. I don't know if there's a built-in PyTorch function to do that type of padding. Maybe there is. Anybody know? Yeah, you can look it up. Could be. You can also hard code it if you want. Yeah. Okay, so let's do a couple of examples. We have an input image of size 32 by 32 by 3. We're going to have 10 5x5 filters with stride 1 and padding of 2. What will the output dimensions be? And just, why don't you take a second and discuss this with your mate.
That's what's that? So it's like others. So imagine the 3 times. Just like an so the output would be sorry. So it's just a vector. It'll be 10 vectors.
Is the padding three-dimensional? Yeah, yeah, the padding is on every edge and on every channel.
And it's 5 by 5, not 5 by 5. Input matrix. 32.
Okay, can you get a show of hands of who thinks they got it? Anyone who wasn't able to figure it out? Okay, let's walk through it with you to make sure we're all getting this. So what did you do at first to try to figure out the dimensions? Do you want to start with the spatial dimensions or the channel dimensions? All right, let's start with the spatial dimensions. That's the scanning height and width. What were your thoughts as far as trying to figure out the spatial dimensions? Yeah, I think that's honestly how I do it. Yeah, just kind of thinking about how it would look scanning this filter over this image. Yeah, so and I also like to think about what the center pixel of the filter would end up. So if we have padding of 2, where is our center pixel of the filter of our 5 by 5 filters going to be relative to the top corner of the image? If this is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, which of these coordinates in the image would correspond to the center pixel of the filter? So that it would be the 3 by 3, you're correct, if we didn't have any padding. But we're going to have 2 layers of padding. So instead of being the center pixel being in the 3, 3 coordinate, it gets moved up 2 up and 2 to the left. And the center pixel of our filter is at the top left corner of the image, the 1, 1 position. Okay. And so if that's the case, and then we go all the way to the right side, where will the center pixel of our filter be on the right side?
1/3.
Top right. And then same for bottom left, bottom right. Okay, so we know we're not going to lose any dimensions due to because our padding is helping us out there, right? What about our stride? Are we going to shrink our input by a stride? No, why not? Because we have a stride of 1, exactly. A stride of 2 would divide the output dimension by 2, but we have a stride of 1, so the output dimension remains the same. So, have any thoughts on what the spatial output dimensions are? 32 by 32, that is correct. All right, now let's try to figure out the channel dimensions. So how many input channels do we have in the image? Yeah, we have 3. And these 5 by 5 filters, what are their dimensions? 5 by 5 by 3. That is a really important point. Good job, Sophie. Yeah, that's a really important point that these filters, they have 3 dimensions. We often just say 5 by 5, but their channel dimensions always match the channel dimensions of the input. And the number of channels in the output, does anyone know how we get the number of channels in the output? It's the number of filters. Yeah, so basically each one of these filters gives us a 32 by 32 by 1 feature map. And then we stat one of those feature maps for each filter. Does that make sense? You good on that? So what would our final output dimensions be? (32 by 32 by 10). Yep. Where 32, the spatial dimensions came from our stride and padding, and the relative size of the filter and the input spatial dimensions, and then the number of channels came from the number of filters. Good. Yeah, Travis.
So why did you said the filter is basically 5 by 5? Why is it not?
Good question. So the question is why, for a single filter, is the output dimension 32 by 32 by 1 instead of 32 by 32 by 3? And that is because when we take that dot product of that tensor, we stretch out the spatial dimensions, then we also stretch out the channel dimensions. And so we flatten that into one big long vector, that 5 by 5 by 3 area, and then we stretch out the entire 5 by 5 by 3 filter and do the dot product between those. And so that results in a single number for if we did each channel separately, then we would end up with 3 different output channels. But because we take all of those channels and sum them together, we only get one output.
Do some shit.
Not quite. So you take the filter, which is 5 by 5 by 3, and you take the region of the image, which is also 5 by 5 by 3. You overlay those tensors with each other, and you pointwise multiply all of the elements in those tensors. And then you sum up all of those numbers across the 5 dimension, the 5 dimension, and the 3 dimension, and you get a single number. And that gives you one number, which you will then, and that's for one region of the image. Then you do that for the entire image, and in the end, you get a 32 by 32 by 1 output activation map. Again, okay. It's not, yeah, it's hard to think in three-dimensional pencils. Yeah, Brandon.
Yeah. So in two-dimensional convolution, the input channels is completely irrelevant to the output size. It will always be the glass.
Correct. Yeah, that's an important point. So yeah, Brandon said that in these types of convolutions, the input channels is completely irrelevant to the output channels, and that is correct. Because it gets squashed. The only thing that determines the output channels is the number of different filters.
And so then, if you know the number of output channels you have, then you know that's the number of filters you have.
Yep, number of output channels is number of filters. Yep. Okay. Question.
And each one of the filters has access to all 3 output channels. Sorry.
I don't know what you mean by randomly distributed, but yes, each filter has access to all 3 output channels. And that's important because we want to be able to mix information across channels. Okay.
Something that helped me out was, although the visualizations are very similar, the kernels and matrices or tensors are different in the way that they interact together. So with the kernels that we have, we're sort of getting a scalar out, but sometimes with the matrices or tensors, we're producing a larger.
Okay, thanks.
So I see. So when you pad in the row and column. Well, why don't you pad in the channel as well? Because there's 3 channels. Why don't you add 2 channels on the side and make 7?
Okay, so the question is, why do you pad on the spatial dimensions but not on the channel dimensions? I'm going to turn the question back around to you. What do you think?
You don't want to. I guess they're color dimensions, so it's hard to determine what colors the other dimensions you're padding represent. So,
yeah, I mean, it's a good question. So why? Yeah, it sounds like you have a thought in the back.
Yeah. Whereas,
So that's a nice thought, but I'm actually going to disagree with you on it. So I would say that the colors definitely have relationships with each other. And so we do want to learn relationships between them. And that's why we have filters that span all of those input channels. The reason why we pad in spatial dimensions is because due to having different strides and different filter sizes, we end up losing spatial. We end up losing spatial dimensions, and so if we want to preserve those, we need to have padding. Whereas, as Brendan mentioned, the number of output channels has nothing to do with the number of input channels. And so there's nothing that makes us lose output channels, if that makes sense. So there, yeah, there's no real reason to pad in that dimension. So this is a more complete formula where we take the output dimension is the length of the input n plus 2 times the number of padding minus the filter size divided by the stride plus 1 gives us 32 spatial dimensions. And then, yeah, how many parameters are there in this layer? That's a good question. Let's try to hear from someone we haven't heard from. Yeah. No. So when we're talking about number of parameters, we're talking about number of neural network weights that we're going to tweak. Yeah, out in the back. So the thought is 32 by 32 by 3 by 10. How do you get that? 5 by 5 by 3 by 10. Why? That is exactly right. Yep. So to repeat that, each filter is 5 by 5 by 3, and we have 10 of them. So the number of parameters is 5 times 5 times 3 plus times 10, which is 750 or 250? 750. Yeah. And so you can see, well, yeah, we're going to do the number of parameters that you would need for a fully connected layer. That would do the same thing. Oh, we forgot our bias. So yeah, that plus 1 is our bias. So it's actually going to be 76 parameters per filter times 10 filters is 760. I don't know if there's a way to collapse this. That's nice. Okay. Yeah, so then for a fully connected, unfortunately, it tells us the answer, but for a fully connected layer, we would have to have the full input image size, so 32 by 32 by 3, because we're going to stretch that out into a vector, and then a weight matrix that is that same size. So actually, I think this might be wrong, because we need to be able to, I think this should be 32 by 32 by 3 times 32 times 32 times 3 times 10. In order to get an output dimension of 10. Point is, though, that's a lot more parameters. And so basically we can think of this convolution as a very, very sparse version of this fully connected weight matrix, where basically we have numbers only where the convolution, each convolutional filter is allowed to look at a region of an image. And it turns out that this model with 760 parameters does just as well, if not better, than this model with over 31 million. So that's a strong argument for convolutional neural networks. Then yeah, just one more thought. Does it make sense to have a 1-by-1 convolutional filter? And if so, what would the intuition for that be? Think about that. Yeah, what do you think the intuition for a 1-by-1 convolutional filter would be. But someone we haven't heard from today. Yeah.
In cases where the spatial dimension of the pixels have no relation between each other.
Yeah, totally. So that's definitely one possibility where that there's no spatial relationship between pixels. That is exactly what that would do. And so what information would we be gaining from that 1-by-1 convolution if we're not mixing spatial information? Well, so we are still having a filter that combines some sort of information. Any thoughts on what that filter would be learning, Michael? Yes, that is it. Yeah, so exactly. So it 1-by-1 convolution mixes information across channels and not spatially. And there are several reasons why you might do that. Maybe because you don't think that there's a spatial relationship between pixels. Maybe because you want to constrain your neural network to do a certain thing at a certain point, which is only mixing info across channels. So yeah, people use 1-by-1 convolutions. Now, the most commonly used type of convolutional filter is a 3-by-3 filter. And people use that size of filter even if they're dealing with images as big as 1024 by 1024. So we're going to think a little bit about why that might be. So here we have a diagram showing an input image that's 5-by-5. And then what each of these visualizes is what region of the prior image this pixel is allowed to see. And so you can see here, when we convolve a 3-by-3 filter by this region, we end up with this pixel right here. When we convolve a 3-by-3 filter with this region, we end up with that filter right there. And so there's a sort of shrinking thing that's going on here. Question, if we were to draw the map of the pixels in this first image that this last pixel can see, which squares would be filled in? Yeah, it would be all of them. That is right. You want to explain why that is?
Because
Exactly. Yeah. So what he said is this pixel sees all of these 9 center pixels, and each of these center pixels is able to see a 3-by-3 window of the original image, which covers the entire input image. And so this is we call this the receptive field of an activation. So the receptive field of a single pixel 2 layers down with a 3-by-3 kernel is a 5-by-5 window. And if we were to take if you were to apply this once more, how big would the receptive field of a single pixel be? If we were to add a third convolution that's able to see 3 pixels here, what would be the receptive field of that single pixel in the original image? Well, yeah, so we're going to assuming that we're allowed to make bigger input images. The receptive field would be 7-by-7, because the first layer shrinks it from 7-by-7 to 5-by-5. Second layer shrinks the receptive field from 5-by-5 to 3-by-3, and so on, and then lastly from 3-by-3 to 1. And so that single pixel is able to take input from as wide a window as 7-by-7 in a 3-layer network. Okay, yeah, Dane.
When is it a better idea to have multiple layers like this where you use a small kernel versus using large layers or a large kernel across one layer? Because
That is the question. Yeah, that is a question. Why? So why is it better to have small filters across many layers versus large filters across only a few layers? Looks like we have a lot of ideas. Yeah, what's your thought? Numerical stability is a thought. Yeah, deeper networks tend to be less numerically stable. That's a possibility. Or well, actually, no, that would be an argument in favor of the larger convolutions with fewer layers. That's an interesting thought though. Brandon. Speed. Yeah, it could be. I haven't run the numbers on the trade-offs, and it probably would depend. But yeah, that's another thought. Yeah.
Would be less like every box that you're like every other one that already out.
Yeah.
So why should now speed is easier to compare a lot of small ones together. That's the cost.
Yeah, that's a really good point. That's along the lines of what Brandon was saying as far as speed is. Yeah, larger filters mean that you have mean that convolutional dot product is going to be more expensive. Yeah, what do you think? Prevent memorization. Interesting. So the idea being that larger filters would probably have a tendency to memorize more complicated features and causing you to overfit, something like that. That's an interesting thought. But continue thinking about this, and we're gonna ask this question again at the end. And we already answered those questions. Yeah, three by three comms gives similar representational power as a single 7 by 7. So yeah, here's the computational answer. So this is running the numbers. So yeah, with a 7 by 7 convolutional filter, we would have 49 times the number of channels squared, whereas 3 by 3 convolutions is 27 times the number of channels squared. So yeah, fewer parameters, cheaper, plus more nonlinearities in between per number of parameters while preserving the same receptive field. Yeah, one other thing that I would kind of argue along the lines of, remind me your name? Brendan? Okay, yeah, along the lines of what Brendan was saying is I think that having more filters that are smaller allows you to learn, allows basically a greater variety of patterns to be learned than yeah, a single large convolutional filter. That's just my intuition. So summarize convolutional layers, take an input of size, weight times height, or width times height times number of channels. Each convolutional layer requires 4 hyperparameters, the number of filters, the spatial dimensions of that filter, the stride, the step size, and the amount of padding. And then we have a formula which gives us the size of the output volume. So some common choices. It's often, yeah, common to use filters of size between 1 and 5 in spatial dimensions with padding that center, as I was saying, centers the middle pixel of the filter at the top left corner of the image. So padding of 1 for 3 by 3, padding of 2 for 5 by 5. And then you can also add in stride if you want to shrink this spatial dimensions. And then, yeah, as far as the number of kernels, it's often common to try to shrink the spatial dimensions and extend the number of channels. And so, yeah, often you'll see things where you have kernels with a stride of 2 that shrinks the spatial dimension by 2 and doubles the number of channels. So you'll go from 3 channels to 8 channels to 16 channels to 32, 64, etc.